All right, yeehaw! Last topic of Unit 2, and some of you remember this acronym and are probably having some flashbacks. We're also adding in bond hybridization, and for those of you who had me in first year chem, we are adding some more VSEPR shapes. So, whee! Ultimately, this is about valence shell electron pair repulsion theory, which lets us model three-dimensionally how molecules actually exist in the world. So this is all based on electron pairs and how they repulse, right? They repel one another because negatives and negatives don't like being super close. So bonds and lone pairs will arrange themselves in some pretty interesting ways, and they fit certain patterns based on how many domains of bonds as well as lone pairs we have. So a lot of interesting shapes. We have names for all of them. We also have common bond angles that we see for each shape, and you are ultimately responsible for memorizing them, which is kind of a bummer, but if you want to take the AP test, I kind of just want to know them. It's honestly not too bad once you run through a set of flashcards, 3 or 4 times, but yeah, it is what it is. So again, this is determined by how many things are jutting off, meaning lone pairs or bonds, on the central atom of a molecule. So we typically don't do too much VSEPR with molecules that have multiple central atoms, although you certainly can analyze longer molecule chains like stuff you would have seen in biology, big organic molecules. You definitely can analyze the VSEPR geometry, but we're typically just going to be looking at one central atom kind of molecules. So like a little hub in the middle, and then however many things jutting off. Again, the whole goal of how these molecules are arranged is to minimize that electron-electron repulsion. And this is similar to how you can only have one toxic friend per friend group, right? Those negative people, they gotta space themselves apart. Yeah, I don't know what that meme is. I really want to eat a bird, but the birds will not let me. Yeah, am I the asshole? Don't know. Love me some memes. Right. So, when we talk about the repulsion of lone pairs, there are electrons in bonds, right? So a single bond doesn't want to be right next to another single bond unless it has to. So the electrons in bonds are also repelling, right? Trying to spread themselves apart. But we see that lone pairs have a stronger effect on that. So here I've got 3 molecules, methane, ammonia, and water. So methane is CH4. And where is my laser pointer? All right, so, do I not have the pin on this? Yeah, there we go. Okay, so methane is CH4. Oh, this is the crappy slides, I see. Ammonia is NH3, and water is H2O. So what we see here is the relative amount of lone pairs makes the bond angle smaller and smaller. That means this angle, right, is 109.5 degrees. This angle is a little bit less than 109.5 because these guys, these lone pairs, are really just pushing on everything. They're saying, stay away from me, I'm really negative. And then the bond angle between waters, OH and OH bonds, is even smaller because you've got a lot of electron lone pair repulsion. Okay, so this is generally how we communicate it. You don't have to memorize a specific number for something like ammonia or H2O, but knowing that their bond angle will be less than 109.5 or notably less than 109.5 because there are more lone pairs on that central atom. So it's important to emphasize it's not important if there are lone pairs on the outer atoms, right? But just on that nitrogen in the middle or on that oxygen in the middle. Yeah, you can read that. Okay, so when we're determining molecular geometry, the first thing is we need to know what the Lewis structure looks like, and then we're going to count just how many bonds and lone pairs are jutting off of the central atom. If you have something with a double or a triple bond, we count that bond as one bonding domain, just like when we were doing bond order. And then, using a set of things we just memorized, we determine molecular geometry. So it's going to look like, let's see, sorry, not sorry. Oh yeah, another meme. Anyways, it's going to look something like this. So you've got your basic geometry. These are the shapes listed in the first column, referring to the overall electron pair geometry of everything in that row. So, for example, the basic geometry when you have steric number 2, meaning there are two things jutting off the central atom, the only shape for this is linear, right? You've got one bond there, and that's it. No lone pairs. Well, you're looking at a line, buddy. But as soon as you get to a steric number of 3, again, there's 3 things sticking off the central atom now, but still 0 lone pairs. You have either trigonal planar, or if one of those bonds is a lone pair, you get this bent or angular shape. Again, note how the bond angle is slightly less than 120 degrees, as it was in trigonal planar, because you've got this lone pair pushing on things, right? It's pushing them down. And then as the steric number increases to 4, 5, and 6, we get even more shapes because there are even more places to have one lone pair, or maybe you have 2 lone pairs, maybe you have 3 or 4, right? So we get a lot of interesting shapes. Folks who had me last year, I only required you to learn steric numbers 2 through 4. So steric numbers 5 and 6 are new. And these are really only possible with that expanded octet we talked about in our Lewis diagrams. So only with the advent of expanding how many electrons your central atom can have beyond just 8 can we access some of these more complicated shapes. Again, flashcards, Quizlets, reciting every night, stick and poke on your forearm, whatever you got to do. You need to know the shapes and the angles for all these things. Now, that being said, it is kind of a lot, and looking at this diagram seems really in a vacuum, like not that relevant to what we've been talking about in the course, right? Where are the chemical formulas? So what I want you to do is go to a website like this one. You can type this in, or you can just look up VSEPR, and I'll show you what that looks like. It's going to be, let's see, VSEPR. You get this really cool interactive simulation. We're going to click real molecules, and I can look at, right now I'm looking at H2O, right? I see it's got a steric number of 4 because there are 1, 2, 3, 4 things sticking off of it. I can also show the bond angle and see, hey, that's less than 109.5, right? And that's because of those lone pairs. If I look at CH4 methane, right, steric number 4, but all those bond angles are exactly 109.5. There's no lone pairs on the central carbon, squishing them closer together. But I can also go to something more complex like phosphorus pentachloride, right? Now this has a steric number of 5, okay? And I see 2 different bond angles, right? There's this 120-degree angle sort of around this central pillar, and then there's 90-degree angles between everything else. So 2 bond angles between this guy. And you can also click down here to toggle on what's the name of the molecule geometry, as well as the electron geometry. So I really recommend using this to kind of tinker around with like, well, what are these different shapes? What do they look like? Oh, this is trigonal bipyramidal, right? So a steric number of 5 things jutting off, but with 1 lone pair, it becomes a seesaw, right? So you get these very, it's not tactile because you can't pick these up and hold them, but more tactile than just looking at a flat 2-dimensional chart like I have in the slides. So I highly recommend, maybe in between doing some flashcards to learn the names and the angles, look at something like this to see, okay, I've got this smaller than 120-degree angle around the middle, and then these smaller than 90-degree angles sort of jutting vertically out on the seesaw shape. So again, something to mess around with. All right, so back to it. We are going to pivot a little bit to talk about bond hybridization. So this is a new thing for everyone. So one of the things we do when we're trying to explain why we have this 3-dimensional geometry is we assume that orbitals mix together to form what we call hybrid orbitals. So we've talked about s orbitals and p orbitals. Those form our valence shell, right? Your s and p orbitals, they hold 8 electrons all together, and they can actually hybridize together to mix the shapes. So we didn't talk too much about this, but s orbitals are basically spheres, and p orbitals are basically peanuts or or sometimes called a dumbbell. So s orbitals tend to look like this. P orbitals tend to look like this. Right? So they're a little longer, and they sort of have this meeting point in the node. That node in the middle is generally going to be your nucleus. Now, when you have a bunch of s and p orbitals, because again, there's 3 p orbitals that we can have, and so they go up and down, and there's one that sort of goes like out. It's hard to demonstrate. When all 4 of these orbitals combine, they basically mix their shapes. They mix the spaces that electrons can occupy when they are involved in bonding. Okay, so how do we notate hybridization? We do it with a pretty simple notation that basically refers to how many things are jutting off that central atom. So similar to when we determine, as the steric number 3, steric number 4, blah, blah, blah. We're just kind of counting how many domains are bonding around that central atom. So to find the number, we take, well, let's just look at this example, methane, right? So we've got 1 carbon with 4 hydrogens. Now, carbon has access on its second energy level to a 2s orbital and 3 2p orbitals, right? Now, since it has 4 bonding domains, rather, sticking off of it, all 4 of those orbitals are going to be involved in bonding, and they mix so that each of them is what we call an sp3 hybrid orbital. So the number of hybridized orbitals is equal to the sum of exponents in the bond hybridization. So what do I mean by that? Sum of exponents in, I'm just going to write bond hyb. Well, S has an exponent of 1, P has an exponent of 3. 1 plus 3 is 4. So the number of hybridized orbitals is 1, 2, 3, 4. You're really just counting bonding domains. That's kind of it. So let's see, the sum of the superscripts, right? Blah, blah, blah. All of that you will need to know for this course is SP, SP2, and SP3 hybridization. It gets a little more complicated when you go to steric numbers 5 and 6, but you won't be responsible for knowing those. So if we look at ammonia, NH3, right, we've got N, 3 H's, and a lone pair on the nitrogen. How many bonding domains are there? 1, 2, 3. So the sum of superscripts is going to have to equal 3, so it's going to be S1P2. That is the bond hybridization for ammonia. Honestly, not too hard, but it is a weird thing. We also need to talk about sigma and pi bonds, and yes, you may make one sigma joke. I really am bummed I'm not teaching this in person, so I could hear you guys chuckle. So sigma bonds are the first bond. They're gonna that forms between 2 atoms. It's going to be the most direct route. This is going to be your single bond. When you have a double or a triple bond, that shortest route between the 2 atoms, what's noted in green here, that's already occupied space. So your double bond or your triple bond needs to sort of go above or outside where that single bond is, and that forms what we call pi bonds, and that is made from the p orbitals, those dumbbell shapes, basically stretching out above or stretching out to the side of where the single bond has formed. So anytime you have a double bond, you've got 1 pi bond and 1 sigma bond. Anytime you have a triple bond, you've got 2 pi bonds and 1 sigma bond. And again, this is really just like a counting game, so we'll do some practice with this. If you're interested in learning more, you can look at the slides and click this link. There's some really cool stuff, but really all I'm going to be looking at is, can you identify bond hybridization, so SP, SP2, and SP3, and can you correctly count and identify how many sigma and pi bonds are present in a molecule given its Lewis structure. So let's do some practice. Again, if you want to learn more, go to this link from Florida State. It's pretty cool. Oh, also something from Chem LibreText. We've already talked about this stuff. Yeah. Yeah. Okay. Oh yeah, polarity. So before we get to some practice, we have talked about covalent bonds that have different electronegativities, right? And the greater the difference in electronegativity, the more electrons are going to be hogged by one element. Now, when we talk about polarity, we can talk about the polarity of a bond as well as the polarity of a molecule. So right here, I've got HCl, and I'm indicating the polarity of the bond by putting this positive arrow where the positive sign is by hydrogen and the non-positive sign is by chlorine. I can also indicate it using these lowercase delta signs. So delta positive by hydrogen, delta negative by chlorine. Chlorine gets the negative because it is more electronegative. It is going to hog more of the electrons in bonding closer to it than hydrogen will. And that's what we see in this visual, is that chlorine has this bigger radius with more electron density. Now, overall, this is going to be a polar molecule because this dipole moment, that's what we call this sort of polar arrow or these partial squiggles. This dipole moment isn't canceled out symmetrically based on what we know about the shape of this molecule, right? This is just one line, right? H to Cl. There's no three-dimensionality to it. It's just like boop, boop, and there's more electrons on the chlorine. So what happens when we don't have a dipole moment, or when we do have a dipole moment cancel out? Well, we get something like we see in carbon dioxide. So carbon dioxide has two oxygen double bonds with carbon, and carbon is less electronegative, right? So it's got the more positive relative charge on it, and each oxygen has a partial negative. But this does not have a molecular dipole. It is overall a nonpolar molecule, even though it has two very polar bonds. Carbon and oxygen, it's a pretty polar bond. But overall, it is nonpolar because it is a linear molecule, and the dipole moments cancel out. If we look at H2O, however, we know that H2O is, well, I'm going to butcher a 3D drawing, but we can look here. H2O is not a flat thing, right? So having these two bonds that have a partial positive, so these are the two hydrogens, with these lone pairs there, it means this side of the molecule, this side right here, is very positive, and this side is very negative, right? All those electrons are concentrated there. So we get an overall dipole moment in H2O that is going to be a lot more negative on this side and a lot more positive on the hydrogen side. So a lot more negative over here, a lot more positive over here when you think of those two. All right, so we're going to do a couple examples. I know this video is kind of long, so I won't do all of these. Yeah, so I'm going to do an A, and then, well, tell you what, I'm going to cut this video here and then just upload just the practice. Okay. Sorry about that, y'all.